Myself Mohana Mukherjee from the branch of Electronics and Communication. Today I am here to discuss about the topic metal oxide semiconductor field effect transistors that are generally termed as MOSFETs, about its comparison, structure and advantages. Before discussing about the structure of the MOSFET, I would like to tell you what a MOSFET is. It is the most commonly used field effect transistor in both digital and analog circuits. It uses channel of P or N-type semiconductor named N-MOSFET and P-MOSFET respectively. Silicon is the main choice of the semiconductor that is being used. However, silicon germanium is used by some common chip manufacturers. Some of the other commonly used semiconductors such as gallium arsenide are not useful in MOSFETs because they do not form good gate oxides. At the gate terminal, it is composed of a layer of polysilicon, and on top of that there is a layer of silicon dioxide which acts as an insulator in between the gate and the conducting channel. When in operation, a potential is being applied in between the source and the gate terminals. There generates an electric field through the oxide layer, creating an inversion channel in the conducting channel, also known as the depletion region. The inversion channel is of the same type as that of the source and the drain, creating a channel in which current can pass through. By varying the potential in between the gate and the body, this channel in which the current flows can be altered in order to allow more or less current to flow through depending upon its size. Comparisons that are made in between a BJT and a MOSFET. BJTs, they are a bipolar device and they also follows RTL logic, and MOSFET, they follow CMOS logic. RTL logic, here resistor acts as input terminal and transistor, it acts as a switching device. The MOSFET also consists of a very high amount of input impedance, and this particular phenomena is known as fan-out. The CMOS static dissipation is low. In BJTs, they have a higher transconductance. You can see here the comparison is made in terms of the transconductances of a BJT and a MOSFET. In terms of BJT, here this particular term KT by Q is present. Here in MOSFET, the term is VG minus VT by 2. Obviously, since there is a difference made in between the gate voltage and the threshold voltage, its value is much less as compared to the transconductance of a BJT. In today's MOSFET, the drain current is very much higher for fast switching circuits that requires a ballistic operation. Importance of these circuits, that is the VLSI or the LSI circuits. First of all, it has a low fabrication cost since its size is very much less as stated here. Since it has a low fabrication cost, its transportation cost is also reduced, and it also requires a very less amount of storage area. And this particular devices also consist of low power consumption. These are some of the basic properties that are stated. The first one is the unipolar device. Since it is a unipolar device, only electrons or holes will contribute to its current flow. And the next one is that it requires a very high amount of input impedance. Input impedance, the DC input impedance is very high here. It is capable of a high power gain. It is a 3 or 4 terminal device, that is the gate, source or drain. And the last one that is stated here, it is a body substrate. At some cases it may be considered, in some cases it is considered. It consists of two important modes, enhancement type mode and the depletion mode. And two channels, as we all know, either it can be a P channel MOSFET or an N channel MOSFET. These are the symbols of a P channel MOSFET and an N channel MOSFET. These are the three terminals in both the cases, drain, then gate, and this is source, and this one is the body substrate terminal. This is the operation of the MOSFET that is stated in terms of the VI characteristic curve. Here, the main three regions are stated by these letters A, B, and C. In A, we denote the cutoff region or the subthreshold region. This terminal B, it denotes the linear region, and this terminal C denotes the saturation region. A voltage is present in between this B and the C, or we can say between the linear region and the threshold region. That is the pinch of voltage. The linear region and the saturation region consist of this particular pinch of voltage, which is discussed later, and this particular region, that is the linear region, it at times acts as a resistor also. Also along with this, we can say that the MOSFETs are only operated in the linear mode only, whereas in the saturation region it is reserved for analog circuits. Explanation of these regions that was discussed in the previous characteristic curve are stated here. The first one is that of the in case of the N plus Pn plus structure, here we can see that the ID current is 0 and the VGS is also equal to 0. So, a recombination of electrons and holes between the gate and the source takes place, but there is no inversion taking place. It remains the same. The P-channel MOSFET remains the same because the gate terminal, it does not have the strength to form the recombination. Then, the next step is the same of the N plus Pn plus structure. Here also ID current is equal to 0, but then a gate current has a little more capacity than the previous one. So the body, source and the gate are following a recombination here, but a drain current, it remains as it is. In the third structure here, we can see that the VGS is much greater than VT and the inversion here takes place from a P channel to an N channel structure. It is discussed in the next slide. From the previous slides, we have found out that VT, it is obviously denoted as the threshold voltage. Now, if VGS is less than VT, then it has a very less amount of positive charge on the gate in order to invert the P-type region to the N-type region. And this particular region is known as the cutoff region. That was A part in the graph. In the second part, we have seen that inversion is taking place, creating an N channel in between the source and the drain. And here the P channel is been inverted to the N channel only because there is a sufficient amount of charge present on the gate in order to attract the electrons and invert the P type. The MOSFET is therefore on condition. We have two modes of operation, the triad region and the saturation region. Discussed here. Triad region. Coming to the triad region, a voltage control resistor is obtained at a very small amount of VDS. Obviously, these three structures are present corresponding to it. A curve on the ID and the VDS is given. Here we can see there is an increasing amount of VGS. Reason is that it allows more amount of drain current to flow. Here in the first structure, when we see that the increasing amount of VGS is not much as compared to the third structures. In the third structure, if you see, there is a more amount of drain current that is flowing, that is compared to that of the first structure, and that is denoted by this curve. And this is the triad region that is described. Coming to the saturation region, it occurs at a large amount of VDS. Previously, we have always seen that this metal oxide semiconductor layer always used to form the shape of a capacitor, forming a dielectric medium in between them. But here the difference occurs. Here you can see there is a tapering end that is occurring in this channel. The reason is the increasing amount of VDS, and here is the saturation region that is taking place in this part. And in the saturation region, in this mode, the switch is on and it starts conducting. However, since the drain voltage is higher in this case than the gate voltage, a part of the channel it turns off, and this mode corresponds to the region which is also known as the pinch off voltage. Therefore, we see that there exists a voltage in between the linear and the saturation region that is discussed afterwards. Coming to the saturation region curve, here you can see the triad region is given, and this is the saturation region that is present. Now, what is a pinch off? Every time when we talk about the saturation region, the term pinch off arises. What actually is a pinch off? The pinch off region occurs in a MOSFET when it stops operating in the linear region and the saturation when the linear region it starts operating and the saturation region it occurs. Now, suppose initially we get an increasing amount of current whenever we increase the drain bias, but a time will be reaching when we have VD set is equal to VG minus of VT. That is, inversion is disabled in the case, and therefore the pinch off occurs. So, in this case, what happens is that the current saturates. So, even though the charges will flow, but we can't draw more current with higher drain bias. So here is actually where the pinch of voltage comes into action. These are the some equations of the MOSFET. These are some of the simplified ones. For the cutoff, for the triode, this is the one, and for the saturation, this is the one. Here K and dash, it denotes the electron mobility into the gate capacitance, and VT, it denotes the doping concentration and the gate material that has been used. Now, in the previous structures, we have been talking about the capacitance part. What actually is the capacitance termed as? This is the parasitic capacitance which is present. This parasitic capacitance, it actually contributes to the gate current to flow at higher frequencies, and it also limits the speed of the device. Therefore, turning on of the MOSFET on requires the charging on of the gate capacitance. Some of the advancements and limitations of the MOSFETs. Obviously, the MOSFET, it is the most commonly used, MOSFETs are the most commonly used silicon transistors rather than the other silicon transistors because it is the prime building block of the CMOS digital logic circuits. The CMOS circuits are advantageous because they allow virtually no current to pass through them, and therefore they consume very little amount of power. This is done by wiring every P MOSFET with the N MOSFET in such a way that whenever one is conducting, the other is not. This not only conserves energy but also helps to reduce heat dissipation, which otherwise could cause the circuit to fail. Overheating is very much a concern. When considering today's generation, the integrated circuits are used which contains millions of transistors in a relatively small space. The MOSFET, it has become increasingly smaller. Obviously, it has a very small size. In the last couple of decades, we have seen today's MOSFETs, they use ICs that have a channel length of only about 100 nanometers as compared to the previous ones. MOSFETs, which are much smaller, they also consist of two main advantages. The first advantage when we talk about is that smaller MOSFETs allow more current to pass, since conceptually a MOSFET acts as a variable resistor when it is on the on state, and a shorter resistor corresponds to less resistance and energy is being dissipated. Secondly, the gates are smaller, which means that the capacitance is lower, decreasing the amount of time in which it takes the capacitor to charge, thus increasing the switching time and increasing the processing power also. Lastly, smaller MOSFETs, it also results in more transistors per chip, thus either increasing the processing power per chip or reducing the cost per chip. And recently we have found that when talking about the limitations, that the small size of MOSFET has created operational problems as producing tiny transistors and therefore often limited by advancements in semiconductor device fabrication. This is mainly because the amount of voltage that can be applied has to be reduced to keep the device stable. Because of its small size, due to these reduced threshold voltages, when the threshold is turned off, it will still conduct a small amount of current. Therefore, a weak inversion layer starts originating, which consumes power when the transistor is off. Therefore, this is known as the sub-threshold leakage, that is the main obstruction taking place here. Previously, this was not a non-issue with larger transistor. However, in the smaller devices of today, the sub-threshold leakage can result in 50% of the total power consumption of the transistor. So this is one of the limitations that has been found out in case of a MOSFET apart from its advancement that has made in the technology field. Now coming to the conclusion, MOSFETs, as we all know, it forms the primary building block of a CMOS digital circuit logic. Along with that, it also acts as an interface in between an integrated circuit that can give only a tiny current and the motor that takes a big amount of current. It also acts as a complementary pair that using hi-fi power amplifiers, and it also produces less distortion, and therefore integrated circuits can be made more compact in our day-to-day life with the help of the MOSFETs that we use. And that's all about the MOSFETs. Thanking you.